Okay, hi Zach. Welcome to lesson number 97. So you finished a whole week of testing where you had math testing every day, and now we're going to jump back into the lesson. So we'll see. I think this will be a good one for you to jump back into because it's kind of new as far as this textbook goes, but I know that you already know the Pythagorean theorem. So in that way, it'll be a review. Okay, and basically we're going to derive it and show you why it works, okay? So the first things first, Professor Akbar's geometry lesson of the day. It's a trapezoid. Okay. Okay. All right. Thought you'd like that one. Alrighty, now let's jump into talking about angles and triangles first. So what's interesting, the book points out, is that mathematicians sometimes disagree on definitions and terminology, and this is sort of an example of that, the definition of an angle. So as you know, you can have two intersecting lines. There's one line, there's the other line, and they intersect right at that point. And two intersecting lines are going to form four angles, A, B, C, and D. And here's the two intersecting lines and the four angles formed. So now let's focus in on one of the angles. If we only look at angle B right there, we see that it's formed by part of lines 1 and 2. So this was one of the lines, this was the second line, right? And these are called half lines, or they can also be called rays, R-A-Y-S, right? Because they start at a point, there's the rest of the line, they go off forever in that direction. But what the mathematicians kind of disagree on is how do you define this angle formed by those two lines? How do you define angle B? So it points out that Europeans kind of think the angle is this space in the middle between those two lines. So like all of these dots that I'm making here with the red and the yellow dots that I've already made are within angle B and part of angle B, and that space is what defines the angle. But American mathematicians tend to define the angle by the rays themselves. So like this ray and this ray make the angle. And so to them, the angle is kind of the set of points that make up the rays. Okay? And others say that the rays are the sides of the angle, but they don't say what the angle is. So some say, well, it's not really the opening of it at all. It's sort of a rotation of a ray about its endpoint. So what I think that means is here's the endpoint, here's a ray. Now if you rotate the same ray like 45 degrees, it's going to end up here. And so that's what makes the angle. Anyway, I think I've talked enough about that, how there's disagreement about what it is. But anyway, we're going to say that an angle is formed by two half lines or rays that are in the same plane. So that's important. You can't have, two lines here and then one going into or out of the book, right? It's not like a three-dimensional, it's a two-dimensional, same plane. And that they have a common endpoint. Okay, so that's what we're going to do. To begin a quick review of angle measures, we're going to remember that if there are two straight lines, so these are the rays, actually these are segments, so just two straight lines, if they intersect and are perpendicular to one another, so remember what that means, if these lines are perpendicular to one another, then each of the four angles created, A, B, C, and D, they are all going to be 90 degrees. If the lines are perpendicular, the angles are going to be 90 degrees. Okay. And they also point out, instead of writing out the word degree, you can just write that little circle above the number. I know that you already know that. Okay. Yeah. That's it for that. Okay, so with this definition of a 90-degree angle, it can be proved by using geometry that the sum, this is important, the sum, so if you add up all of the interior angles of any triangle, they add up to 180 degrees. That's kind of cool, I think. I think that's like a really cool thing. But the angles inside a triangle add to 180 every time. So you can already, just by knowing that fact, start imagining some of the questions that they're going to ask you in future lessons, right? So they'll say, this is a 90-degree angle and this angle is 30 degrees. What must this angle be if that's x, right? And then you just add 90 plus 30 and subtract that from 180 and you're going to get 60. And that works every time for any triangle. It doesn't have to be a right triangle. Okay, so with the right triangle though, remember that the side opposite the right angle, so this is the right angle, the side opposite of this is called the hypotenuse. Hypotenuse. It's a long name. It's usually the longest side, but it's the side opposite that right angle. Okay, so that's a definition that you're going to have to know. What is the hypotenuse of a triangle? Now, the other two sides, they're not as fancy. They're just called legs or sides. So either one, just legs or sides. But this one is special. That is the hypotenuse, the side opposite the right angle. So it's not always going to be here. If the right angle were in a different location, the hypotenuse is still going to be opposite of it, okay? Now, here are two other triangles just to show you that the interior angle of the triangles always add up to 180. 60 times 3, 180. What if it's 135 here and you have a 25 here? You could solve for this. It would be 20, okay? So that happens every time. All right, let's jump into 97b, the Pythagorean theorem. A squared plus b squared equals c squared. Remember that on Lego Batman, and he acts it out with his arms and legs, his whole body actually. Okay, so here's a right triangle right here. Okay, I've made a right triangle. Remember that these are perpendicular segments, so that makes a 90-degree angle. Okay, now we're gonna draw squares. I already did draw squares that are on each side of the triangle. So in other words, this side of this triangle is 3 squares long. So since it's a square, by definition, all of the sides have to be the same length. 1, 2, 3, 1, 2, 3, 1, 2, 3. And they are. So I've made a square right here. And I do want you to notice like this little grid system inside the square, because we're going to be looking at the square units of these squares, right? So, and this one right here is another leg of that right triangle, and it's 4 of these segments long. And so if we make a square, it's 4 across, 4 tall, 16 square centimeters, right? And then this one, the hypotenuse, this is the hypotenuse. Now we don't exactly know the length on this one because it's kind of cutting the squares diagonally, but we know it's a square. So this length has to match this length. And in fact, it has to match all the other lengths. By definition, it's a square. Okay, now the square drawn on the hypotenuse of a right triangle, so this is the square drawn on the hypotenuse of a right triangle, has the same area as this one plus this one. That's cool, and that's the whole Pythagorean theorem. So if you find the area of this and you add to it the area of this, you are going to get the area of this is going to be, they're going to add to this area, twice the area. And then remember, how do you get the area of a square? It's A times a, because they're the same length, this is a squared. How do you get the area of this one? It's going to be b times b, so the area is b squared. And what's the area here? It's c squared, which is equal to a squared plus b squared. So that's it. That's the Pythagorean theorem. That's how you prove it. And that is super cool. And that was actually figured out by the early Egyptians as early as 2000 BC. This guy is Pythagoras. This was actually a Greek philosopher and a mathematician, and he's the one that proved this theorem. Anyway, you can read more about him at another time, but that's why the Pythagorean has his name. Look at this little picture here in that picture. That's exactly what we did just now to sort of prove that that's true. Only the hypotenuse of this of this triangle, the way it's shown, the hypotenuse would be, it doesn't let me draw it, would be this guy, right? That's the hypotenuse, because this looks like a right angle. So this would be c squared. Cool, huh? All right. Pythagorean theorem. A squared plus b squared equals c squared. So this is applied to a right triangle. It has to be a right triangle. And c squared is going to be the hypotenuse, or the length c is going to be the hypotenuse of the triangle. So c equals the length of the hypotenuse. I'll just shorten that. And a and b are the lengths of the other two legs. Okay, so let's try it. I just put that there to remind you of a squared plus b squared equals c squared. So what's nice about this, that what I think is really cool, is that they have to tell you what the lengths of two of the sides are, or what the area is, and then you can figure out the third. Because look at this, look at the theorem. Let's look back at the theorem. There's an unknown a, an unknown b, and an unknown c. Whenever you have three unknowns, they have to tell you in the problem, some way or another, they have to tell you 2 out of the 3. And they might tell you C, and they might tell you A, and then you have to figure out B, but they have to tell you 2 out of the 3. And if you know the theorem and you know 2 out of 3, they can't trick you. You're unstoppable. You can figure out the third one, no problemo. So let's do that with example 97.1. It says, given the triangle with the lengths of the sides as shown, so this length is 4, and this length is A, use the Pythagorean theorem to find A. Okay, so we know it's a right triangle, so that's when you start thinking of Pythagoras. We know 2 out of the 3 sides, so we can solve this, no problemo. Let's just start by writing the theorem. A squared plus b squared equals c squared. We're solving for A. Now they could have named that x or whatever, it doesn't matter. So the only trick is, in order to get this right, is you have to correctly identify the legs, which are A and 4, and the hypotenuse, which is that 5. And then you can't get it wrong. You're unstoppable. All right, so let's fill in what we know. Okay, it's going to be a squared, that's going to be one of the unknowns, plus b squared. Now b is going to be 4. Right there, okay? And then we're going to say equals c squared. C in this situation is 5, so it's going to be 5 squared. All right, now I have a squared plus 16 is equal to 25. I subtract 16 from both sides. A squared is equal to 9. And then we use the difference of two squares theorem. So we're going to square root this and square root this. A is equal to 3. But since we wrote that square root, it could be plus or minus 3. But negative 3, when you're talking about a length, does not make any sense. There's no way that it could be negative 3 because you're talking about a length. How do you have a negative length? So we're going to reject that. Rejected, and reject that little sign. And it has to be positive 3. Okay, so the answer is A is equal to positive 3. All right, here we go again. I know you're like, I know how to do this, Mom. Yeah, but you know these examples get trickier. So let's just do another one. What's tricky about this one? Well, the triangle is kind of sideways, so that's weird. So you have to remember that this one is the hypotenuse because it's opposite that right angle. These are the legs, and they gave us 2 out of the 3, so we cannot mess this up. No way we can mess this up. I always write the theorem first. This is how you show your work. Your teachers next year are going to love you if you do this every time. Now we're going to simplify. The P goes here, right? Okay. So I'm going to say P squared is equal to A squared. So I'm going to say A is 4. 4 squared plus 5 squared. And that's equal to 16 plus 25. So P squared is equal to 41. And then we're going to take the square root of that because we're going to take the square root of both to solve for P. P is equal to square root, whoops, yeah, that's fine. Square root of 41. Or it could be, since we wrote that square root, or they just want to make this point. Or it could be the negative square root of 41. But then we're going to reject that because there's no negative length. But technically it could be plus or minus the square root of 41. And you don't have to actually find the square root of 41. You can just write it like this, and that's your answer. Like you could put it in a calculator if you want, but you can just leave it like that. P is the square root of 41. Easy peasy, right? Okay, let's do another one. Here is, I don't know why I put this one here. Where is it? Where is it? Plankton's trying to find something. You're not fooling anybody. Oh, that's why I put it in here, because he says you're not fooling anybody. So take a look at this triangle. So we've got a right angle here. This one's the hypotenuse. Here's the legs. They gave us 2 out of 3 in terms of numbers, even though this is a weird value. But guess what? If they gave us 2 out of 3, we can find that, no problem. All they have to do is give us 2 out of 3, and we are unstoppable. We cannot be tricked, just like Plankton there. I'm going to write it out. Okay, I'm going to make sure I identify them correctly. The square root of 61, this one is C. This one is going to be A, and K is going to be B. All right, so we're actually solving for B squared. So it's going to be 5 squared, that's where that's where this comes from, okay? Plus B squared, I'll just write K squared instead of B squared, okay? Is equal to square root of 61, the whole thing squared. Does that make sense? Okay, now we're going to simplify. So when we simplify, this just becomes 61. When you square the square root of 61, that's like a double negative. It just cancels out. It just becomes 61. So 61 is equal to 25 plus K squared. Okay, makes sense? Now I'm going to subtract 25, K squared is equal to 36. And then square root that, and you're going to have K is equal to plus or minus 6. but there's no minus when we're talking about lengths. They just want you to get into that habit because pretty soon there are going to be things where the negative is relevant. So just don't forget about that, okay? And K is 6. That's our answer. And sometimes you can look back and see, like, does that make sense for K to be 6? I didn't draw this triangle very perfectly the way it shows, but this one's 5, this one's 6, this is square root 61. That makes sense to me. All right, 97.4. I know you're feeling like you got it at this point. I'm sure you do. In fact, I'm gonna delete that because that's really distracting. But here's another right triangle. And what we're gonna do is we are gonna solve for M. And first identify M is the hypotenuse here, and these are the legs. Okay, here we go. Write out the theorem. A squared plus B squared equals, I'm just going to say M squared right here. And then it doesn't matter which one you pick for A or B. It doesn't matter because it doesn't matter. So let's just do 12 squared plus 8 squared equals M squared. And then we're going to simplify that a little bit more. 12 squared plus 8 squared, they took that all the way to, so 144 plus 64, and that's going to be 208 is M squared. So M is the square root of 208. And you can simplify this. Do you remember how to simplify a square root like this? Tell me if you don't. Okay, so you can, okay, remember it's like doing square root of 200 times square root of 8. Or no, I did that wrong. Let's see. Let's erase this. It's going to be square root, two things that multiply together to get 208. It's going to be 64 and 13. No, 64 plus. Oh, shoot. Okay, let me simplify it for you. And it's going to be 4 square root 13. Okay, let's move on. I know you thought we were done with the lesson, but here we go. We are not quite done. I'm going to get back to you on how to simplify this, because I don't know if you remember how, because I'm not sure I remember how, but that simplifies to 4 square root 13. I will get back to you on this. Okay, Pythagorean triples. Now, it is useful to memorize some of these triangles. And the reason why you're going to memorize some of these triangles is because some of them are going to come up a lot. Okay, so for example, this triangle comes up all the time. So if you've got a 3 here and a 4 here, and you do the math, do a squared plus b squared, you're always going to get 5 there. 3, 4, 5. So this is called the 3, 4, 5 triangle. And when you write it like this in triples, you write them in ascending order. So you start with the smallest, go to the biggest. Okay? So notice that all of the sides of these particular right triangles are integers. So it's not a weird like square root 13 number, and it's not a fraction. Okay, so if you have a 5 and a 12, you're going to get a 13 here. Okay? And if you have an 8 and a 15, you're going to get a 17 here every time. So this is 8, 15, 17 triangle. This is 5, 12, 13. And this is 3, 4, 5. And if it is also useful to note that if you have a multiple of 3, 4, 5, so let's double every number, 6, 8, 10, then that also works. It works with the Pythagorean theorem. So it could be a 3, 4, 5 triangle, but the lengths are actually 6, 8, and 10. So if you see something that is 5 and 12, you don't even have to do the theorem because you have already memorized that that goes with 13. And if you see something that is 10 and 24, you don't even have to do the theorem. You can just memorize that this is going to be 26, double that, whatever, right? Same with these, you can just memorize it. So that's why it's useful. Okay, so any multiple of a Pythagorean triple is also another Pythagorean triple. Okay, so let's look at these, a couple more multiples. So a 3, 4, 5 triangle, I drew it above, but a 3, 4, 5 could also be a 6, 8, 10. Okay, but it also could be, so it could be 3, 4, 5. It could be double that, 6, 8, 10. Or what if you take this original one and you triple it? Would that work? Yes, and in that situation you would get 9, 12, 15. Okay, and it would be 9, 12, 15. So that's another Pythagorean triple. So that's why it's useful to memorize this one, especially memorize this one. If you're only going to memorize one, just remember 3, 4, 5. But these are also useful to commit to memory. Okay, so this, what makes it useful is that sometimes they won't give you 2 out of the 3 in triangles, and they expect you to know that. So he's saying, give me one good reason why I should memorize this. Okay, I'm going to give you a reason. In example 97.5, here's the reason. Okay, so it says, recall the appropriate Pythagorean triple to find the unknown length in each of these following triangles. So they want us to find the unknown here, here, and here. Now they did give us 2 out of the 3, so you could do a squared plus b squared equals c squared, but you might have memorized those numbers, those triplets, and if you do memorize them, then you might remember that this one here, you see that 5 and 12, and you'll know that it goes 5, 12, 13. So that means that A equals 13. The only trick is you have to make sure you're remembering the numbers in ascending order and that you know which one is the hypotenuse, right? Okay, so on this next one, this middle one, you look at the numbers. You've got an 8 and you've got a 17. That was one of the ones that they wanted you to memorize, and that was called the 8, 15, 17 triangle. And so you can see that there's an 8, the next one should be 15, and this one is 17. So as long as the hypotenuse is 17, then that matches. So B is equal to 15. Okay, now let's look at this last one. This last one, an 8 and a 10. Now that's not in one of the ones that they wanted us to memorize, but you did memorize the 3, 4, 5. And so is this a multiple of that? Right? So if you double 3, 4, 5, you get 6, 8, 10. So now I've got the 8 and the 10, and I know that C must be 6. So C is equal to 6. And of course, if you don't remember the ones that you were supposed to have memorized, you can just do a squared plus b squared equals c squared. Okay, whew, finally. Trust me, you are going to love this lesson. It's actually fun to do a squared plus b squared is c squared because you're going to understand all of this stuff right away, and I think you're going to do really great, okay? Have fun with this math lesson. Bye.